Next concept is elastic constants. So generally we have four elastic constants. So first one is Hinge modulus or modulus of elasticity, and we know from the Hooke's law, within the elastic limit, stress is directly proportional to strain. Therefore, stress can be written as stress is equals to elastic constant or the constant of proportionality into strain. So that constant of proportionality is nothing but Hinge modulus, and it is denoted by capital E. Therefore, E can be written as E is equals to stress by strain epsilon. So next one is modulus of rigidity. So modulus of rigidity is generally represented by capital G, and it is the ratio of shear stress to the shear strain. So G is equals to tau by phi. Tau represent the shear stress, whereas phi represent the shear strain. Next one, bulk modulus. So bulk modulus is represented by capital K, and it is the ratio of direct stress to the volumetric strain. Therefore, K is equals to stress sigma divided by volumetric strain epsilon V. Next, Poisson's ratio. So Poisson's ratio generally represented by mu, and it is the ratio of lateral strain to the linear strain. So lateral strain, so we know if the strain occurs across the member which is perpendicular to the application of load, and the linear strain is the strain which occurs across the member which is parallel to the application of load. So next we are going to derive the relation between the modulus of elasticity and the modulus of rigidity. So to derive the relation between modulus of elasticity and modulus of rigidity, let us consider the square element ABCD, which is subjected to pure shear stress. So due to the application of this shear stress, there is a deformation takes place. So DA dash B dash C is the deformed shape due to the application of this pure shear stress. Now we are going to draw a line, perpendicular line AH. So draw a perpendicular line AH on the line A dash C. So this distance HC is same as the diagonal line AC. Next, so the strain. So due to the application of this pure shear stress, so what happens across the diagonals? So across the diagonal AC, there is an increase in length takes place, but across the diagonal BD, there is a shortening of the length takes place. So therefore, the total strain across the diagonals AC linear strain epsilon. Next, since across the diagonal AC there is an increase in length takes place, therefore it is positive, whereas across the length BD there is a shortening of the length takes place, therefore minus lateral strain across the diagonal BD. So this is across diagonal AC, whereas this is across diagonal BD. Therefore, so linear strain can be written as tau by E, because we are applying shear stress, therefore tau by E, whereas minus, so lateral strain. So what happens? The lateral strain minus, since it is a compressive, minus mu into tau by E. Mu into tau by E. So how to find the linear strain? So we know the general equation for shear stress is load by area, shear load by area. Shear load by area, and so tau can be written as tau is equals to, so load by area can also be written as sigma. So sigma can be written as Young's modulus into epsilon. So therefore, so epsilon can be written as epsilon is equals to tau by E. So this is a linear strain. So next, let us see how to find lateral strain. So from Poisson's ratio, so we know mu is equals to lateral strain divided by linear strain. Lateral strain by linear strain. So mu can be written as mu is equals to, so we have to find lateral strain. So linear strain we got tau by E. So therefore lateral strain can be written as mu into tau by E. So therefore in place of lateral strain we are substituting mu into tau by E. So in this equation we can see, so after simplifying, tau by E becomes common, so we can take it outside. Tau by E is equal into 1 plus mu. Call this as equation number 1. So next, strain along the diagonal AC. So if we consider the diagonal line AC, so this dotted line represent the change in length or increase in length across the diagonal AC. If we see this diagonal, so we know what is the general definition of a strain? Change in length by original length. So in this diagonal line, the change in length is A1H. A1H is the change in length, whereas original length is HC. Therefore, change in length is A1H divided by HC. But we know this length HC is same as AC. Therefore, in place of HC, we are writing AC. So change in length is A dash H or A1H divided by, in place of HC we are writing AC. So A1 dash, sorry, A dash H divided by AC represent the strain along the diagonal AC. So next one, so if we see the diagram, so suppose if the angle is 45 degree, so angle H A dash A is 45 degree. So if we consider the cos 45 adjacent side by hypotenuse, so adjacent side is A1H, hypotenuse is A dash A, and cos 45 degree is nothing but 1 divided by root 2. So therefore A1H becomes A1H or A dash H is equals to AA dash into 1 divided by root 2. And from this diagram, the diagonal AC is common for upper triangle and lower triangle. If we consider the upper triangle, so AC can be written as root of AB square plus BC square. But we know the sides are small a, length of the sides are small a, therefore, so in place of AB we can write small a, in place of BC we can write small a. So this becomes root 2 into a, therefore AC can be written as root 2 into small a. And from the equation we know that the strain along AC is a dash, that is in place of a dash h, a dash h, that is change in length is a dash h. So in place of a dash h we are writing a dash into 1 divided by root 2 divided by original length AC. So in place of AC we are writing root 2 into a, root 2 into a. So therefore, so root 2 into a. But so from the triangle DA dash A, triangle DA dash A, so tan phi can be written as tan phi, opposite side by adjacent side. So opposite side is A dash, A dash, adjacent side is AD. So AD is nothing but small a, therefore A dash can be written as small a AD and tan phi, tan phi. So therefore in place of A dash we are substituting A into tan phi. So A get cancelled. Therefore tan phi divided by 2. So if phi value is very small, so we can write phi divided by, in place of tan phi we can write phi divided by 2. Call this as equation number 2. From modulus of rigidity we know capital G is equals to shear stress divided by shear strain. So therefore shear strain can be written as phi is equals to tau divided by G. So substitute this in the equation number 2. So it becomes tau into 2 times of G, tau into 2 times of G. So call this one as equation number 3. Now we equate 1 and 3. So this is equation number 1, sorry, equation number 3, and this is equation number 1. So after simplifying, so tau get cancelled. So we got Young's modulus capital E is equals to 2G into 1 plus mu. So this is the relation between Young's modulus and modulus of rigidity. So next one, let us see what is the relation between Young's modulus and bulk modulus K. So to derive this equation, let us consider a cube which is subjected to tensile load across all the 3 dimensions, that is tensile load across, or the tensile stress across x-axis, tensile stress across y-axis, and tensile stress across z-axis. So therefore the strain, total strain along x direction. So what happens due to the application of tensile force or tensile stress across the x-axis, there is a compression which takes place across y-axis and compression which takes place across z-axis. So therefore the total strain across x-axis becomes epsilon x is equals to, so linear stress or linear strain minus, so this is along x-axis, therefore stress by E, linear strain, whereas across y-axis there is a compression takes place due to the application of tensile stress across x-axis, therefore minus lateral strain mu into sigma by E. Then what happens across z-axis? There is a compression, therefore lateral strain sigma by E. So this is sigma x, sigma y, and this is sigma z. So what happens? So we know sigma x is equals to sigma y is equals to sigma z. Therefore, sigma by E is constant 1 minus 2 mu, 1 minus 2 mu. So this is across x-axis, strain which is induced across x-axis. So similarly, across y-axis we'll get the same equation, across z-axis we'll get the same equation. So therefore, the volumetric strain, so we know volumetric strain epsilon v is equals to sum of strain across the different direction, epsilon x plus epsilon y plus epsilon z, epsilon x plus epsilon y plus epsilon z. Therefore, we will get the equation 3 times of sigma by E, 3 times of sigma by E into 1 minus 2 mu, 1 minus 2 mu. So by the definition of bulk modulus, we know K is equals to direct stress divided by volumetric strain, direct stress divided by volumetric strain. So after substituting the direct stress sigma and volumetric strain 3 times of sigma by E into 1 minus 2 mu. So after simplifying this equation, we got Young's modulus E is equals to 3 times of bulk modulus K into 1 minus 2 mu. So this is the relation between Young's modulus and bulk modulus capital K. So next one, relation between modulus of elasticity, that is capital E, shear modulus G, and bulk modulus K. To derive the relation between E, G and K, so we are going to consider the relation between Young's modulus and G and Young's modulus and bulk modulus K. So we have already derived these two equations. So directly we are considering those two equations, that is E is equals to 2G into 1 plus mu. This is the relation between Young's modulus and shear modulus G, and E is equals to 3K into 1 minus 2 mu. This is the relation between Young's modulus and bulk modulus. Now we are going to equate these two equations because Young's modulus is common for both the equation. So after equating 2G into 1 plus 2G into mu is equals to 3K into 1 minus 3K into 2 mu. So it becomes 6 into K mu. So we are simplifying this one. So we are taking mu outside. So mu is equals to 3K minus 2G divided by 2G plus 6K. Next, so we are going to substitute this mu equation either in the equation number 1 or equation number 2. So we are substituting equation number 1. Therefore, so E is equals to 2G into 1 plus, in place of mu we are substituting this one. Then after simplifying this one, we got E is equals to 18 into G into K divided by 2G plus 6K. So from this 2G plus 6K we can take 2 common. So therefore 2 9s are 18. The final equation becomes 9GK divided by G plus 3K. So this is the relation between Young's modulus, modulus of rigidity, and bulk modulus. So now let us solve the problem. A 500 mm long bar has rectangular cross section 20 mm by 40 mm. This bar is subjected to first one 40 kN tensile force on 20 mm by 40 mm face. Second one 200 kN compressive force on 20 mm by 500 mm face, and 300 kN tensile force on 40 mm by 500 mm face. Find the change in volume if Young's modulus E is equals to 2 into 10 power 5 Newton per millimeter square, and Poisson's ratio mu is equals to 0.3. So this is the given figure. So in this figure you can see, so this is x-axis, and this is y-axis, and this is z-axis. Three mutually perpendicular directions are given, and across x-axis there is a tensile force, across y-axis there is a compressive force, and across z-axis there is a tensile force 300 kN is acting. So the first step is we have to find the stresses which are acting on three mutually perpendicular faces. So across x-axis, sigma x is equals to load by area. So across x-axis load we have 40 kN, therefore 40 into 1000 divided by area is 20 mm by 40 mm. So therefore 20 into 40. So we got 50 Newton per millimeter square, and it is a tensile stress. So next one, across y-axis, so we have sigma y is equals to load by area. Load is 200 kilonewton, therefore 200 into 10 to the power of 3 divided by area is 20 mm divided by 500 mm. So after simplification we got a 20 Newton per millimeter square, and it is a compressive stress. And across the z axis, so we have load is a 300 kilonewton, therefore 300 into 10 to the power of 3 divided by area is 40 into 500, 40 into 500, therefore so after simplification we got 15 Newton per millimeter square, and it is a tensile stress. So next, so we have to find the strain across any one direction. So I'm considering the strain, that is total strain across or along x direction. So what happens? Sigma x is equals to, so linear strain across x axis, therefore sigma x divided by E, sigma x divided by E minus, because lateral strain due to the application of tensile load across x axis, there is a compression across y axis and compression across z axis, therefore negative. So and so we have to see for the next direction, that is y axis, so we are applying compressive load, therefore minus again, since it is a lateral strain, mu into sigma y divided by E. Next, again minus because it is a lateral strain. Next we have to see the direction of the load across z axis. So across z axis we have tensile load, therefore plus mu into sigma z divided by E, sigma z divided by E. So we are going to substitute the value. Sigma x we got 50, so here substitute 50, and mu value is given, mu value is 0.3, substitute 0.3, and sigma y is 20, substitute here 20, and here sigma z is we got 15, so therefore substitute 15. So after simplification we got epsilon x is equals to 51.5 phi E. Similarly, the strain across y-axis epsilon y, that is due to the application of tensile or compressive load across the y-axis, there is a changes which takes place across the other two directions. Therefore, across x-axis there is a change which takes place, therefore negative, and it is a lateral strain, therefore mu into sigma x by E, because it is a lateral strain. Next, plus, because linear strain across y-axis, we are finding the total strain across y-axis, therefore in the same direction we will get the linear strain, but it is a compressive load, therefore negative sigma y divided by E. Next, minus, because across z-axis there is a change in shape, then it is a lateral strain, and it is a tensile force, therefore plus mu into sigma z divided by E. So after substituting the values of mu and sigma x, sigma y and sigma z, so we got epsilon y is equals to minus 39.5 divided by E. So next, so to find the total strain across z-axis, so we are going to consider epsilon z is equals to, since we are applying tensile load across z-axis, so therefore there is a changes which takes place across other two direction. So across x-axis there is a lateral strain, therefore mu into sigma x divided by E, again negative because lateral strain. So across y-axis we have compressive load, therefore minus mu into sigma y divided by E. Across z-axis it is a linear strain, therefore plus sigma z divided by E. So after simplifying we got epsilon z is equals to 6 divided by E. 6 divided by E. Next, so we know volumetric strain epsilon v is equals to epsilon x plus epsilon y plus epsilon z. So after substituting the values of epsilon x, epsilon y and epsilon z, we can take 1 by E as common into 51.5 minus 39.5 plus 6. So it becomes 18 by E. And we know volumetric strain is change in volume divided by the original volume. Therefore, change in volume can be written as change in volume is equals to volumetric strain into original volume. So we got the volumetric strain 18 by E. So 18 divided by E. Young's modulus given is 2 into 10 power 5, and the total volume of the given Object is 20 into 40 into 500. So after simplification we got the change in volume 36 millimeter cube.